All right, so I'm here to talk about B3, which is on development of new inexpensive disposable sensor with specific utility for small. We chose microelectrodes is because of the small size and that we could put these small electrodes in different parts of the small water system or other bioreactors for other type of applications. So one type of electrodes we used is the carbon fiber microelectrodes of 10 micron diameters, and panel A is the unmodified electrode, and panel B is after silver modification, basically electrochemical deposition of silver onto the carbon fiber electrode, and C is basically a magnified, the larger scale SEM image of those nanostructures. In addition to carbon fiber, we also use silver wire microelectrodes, 15 microns diameter. Again, panel D is the unmodified silver electrode. Panel E is after silver modification. And panel F is the up-close image of these silver nanostructures. As can be seen in here, these nanostructures are very much like dendrites, which is what we want. We would like to have high surface area electrode materials. In addition to to have these electrodes materials in a nanostructure format, another advancement we have in here is that we use pulse amperometry to grow these materials. Basically, pulse the potential back and forth to grow these structures. And we also added a complex agent, which is ammonium sulfate, to actually grow nanostructures that are very stable on the electrode surface. We do know that these electrodes will eventually be exposed to continuous flow on whether it's a fast flow or slow flow of water. So we want to make sure that these nanostructures will not be easily removed from the electrode surface. So we have two advances, making the nanostructure high surface area, and we also use a method to grow nanostructures that are very stable on the electrode surface. And this work is published in 2015. And here's just another view of how we actually made these electrodes. On the left-hand side is a commercially available carbon fiber electrodes. Ours are not as pretty, but a lot cheaper, that we make our own. We basically seal the carbon fiber or the silver wire into a glass capillary. We then expose the electrode and electrode deposit the silver nanostructures onto it, and that's basically how we make our electrodes. In addition to using SEM to analyze these materials, you can see that it's a nanostructure materials with high surface area. We also use electrochemical approach to analyze that. We analyze the capacitance, the double layer capacitance of these electrodes in the absence of the silver modification and after the addition of the silver. On the left-hand panel, that's for the carbon fiber electrode. The solid line is without silver modification, and the dotted lines after silver modification. We observe an 8 times increase in the surface area, which correlate to the images we obtain using SEM. And on the right-hand panel, and that's the silver electrode, unmodified silver electrode, and the silver modified silver electrode, we were able to grow a bit more materials, even though using the same deposition methods, around 15 times increase in the surface area of this compared to the bare electrode. Well, next we're interested in whether it will work well for nitrate reduction. So we obtained those response curves using in cyclic voltammetry, and that's for the silver modified carbon fiber electrode. On the left-hand side is a dose response curve, and the right-hand side are the actual cyclic voltammogram we observe. You can see that we clearly can observe a large nitrate reduction peak at around negative 1.0 volts. And the limit of detection for this silver on carbon fiber electrode is around 5 micromolar of nitrate. And we also did the same for the silver modified silver microelectrode. And at a glance, they are very similar looking, both in terms of the voltammograms and also the detection limit. The detection limit is around 3 micromolar, slightly better than the silver on carbon electrode. But I would like to show some values here is that 10 ppm nitrate, which is the EPA value as nitrogen, equals to around 45 ppm nitrate as NO3. That corresponds to around 726 micromolar of nitrate, which you can see towards the end of that calibration plot. And the EPA certified method, this method using the cadmium reduction, basically the flow injection system has a dynamic range of 0.2 to 20 ppm, basically nitrate as N, and that corresponds to around 14 to 1400 micromolar of nitrate. So that range is basically similar to the type of the dynamic range that this nitrate sensor can afford. So and also with this sensor clearly be able to differentiate between concentrations that hovers around the EPA value, the 10 ppm values. In addition to analyzing or characterizing the detection limit and also the linear dynamic range, we are interested in determining whether this sensor could be used in real complex samples. So here we analyzed the sensor's response to nitrate in a synthetic aquifer sample, and that's a sample from this reference from this Department of Interior publication in 2001, and containing various concentrations of magnesium, calcium, and sodium, etc. And that's the sensor's response. This is silver modified carbon fiber electrode. In the absence of nitrate, that's the dotted line, and in the presence of nitrate, it's that solid curve. In addition to using cyclic voltammetry, we also use chronoamperometry. Basically, it's an approach that might be slightly easier or more user-friendly because you don't have to scan the whole potential range from negative 0.6 volts to negative 1.2 volts. You can just sit at the potential at negative 1.1 volts and obtain a scan in the absence of nitrate, that's a dotted line, and in the presence of nitrate, that is the solid line. The same goes for the silver modified silver electrode, again, sensor in the absence of nitrate and in the presence of nitrate using cyclic voltammetry and also chronoamperometry. You can clearly see a big differences between the sensor in the absence of nitrate and in the presence of nitrate. These results clearly demonstrate that the sensor could be used in a synthetic aquifer sample, and also looking at these values right here is that these samples are actually this synthetic sample is actually quite low in ionic strength. One of the merits of this sensor is that it's not very particular about the ionic strength of the solution, which is good because in general I would not expect relatively clean water to have a lot of ions in there to have a very high ionic strength. So next, now that we have developed these sensors on microelectrodes, we are also interested in developing these sensors on paper-based electrode, which is the original plan for this proposal, is to develop nitrate sensors on disposable paper electrodes. And we have demonstrated that we could do that as well. So panel A is basically a handheld potentiostat that one could use. And panel B, it's a small device that we developed for these paper-based electrodes. And we could confine the minimum volume to use that small device. The small cell is 10 microliters. And on the next part is the actual electrode that's been modified, the working electrode being modified with silver nanostructures. And panel C, again, shows the SE image of these silver nanostructures. When compared to the ones that shown in the previous slides, you can tell that the structures are very similar, independent of whether it's being deposited on microelectrode, silver or carbon fiber, or this basically screen printed carbon electrode. Basically, it's graphite powder mixed with mineral oil. It's a very, very cost-effective approach. At this stage, we're buying it commercially around about $1 a piece because we are not buying it in bulk, but we could also develop it. If fabricated in bulk, the cost will decrease. But what we were most interested is how well it will work in the presence of nitrate. And we did a very interesting experiment here. It's actually using sulfuric acid acidified samples that we obtained from the Nebraska Public Health Environment Lab. Thank you, Bruce, for helping me to obtain these samples. And Mary Bowden from this lab gave me 40 samples of nearby Lincoln waters with well-defined concentration of nitrate. She used the Latrat method, which is also the same as the EPA 353.2 methods, and to analyze the nitrate concentration. And these samples are acidified with sulfuric acid to pH 2. The only information she could provide is the nitrate concentration, so I have no idea of what other ions are in those samples, but I asked my student to run the samples anyway, so we chose 6 different samples without knowing what are the matrix contaminants in there or how clean it is. We ran it and we realized that the concentration, if the samples got about twice the amount of concentration of each other, for example, around 6 ppm versus around 12 ppm, we were able to obtain linear correlations between these samples, which was unexpected. But it also just suggests the fact that this sensor is not very much affected by the type of the pH, not the pH, I mean the ionic strength or what other composition of that water sample, and we will still be able to analyze the nitrate concentration in the samples. Last but not least, although these samples were these results were obtained using the single pixel carbon paper-based electrode. We have also for another project we developed multi-pixels, including the 3 pixels as well as the 6 pixels carbon electrodes that would enable simultaneous detection of 3 different water samples or the same samples, but be able to detect to obtain 3 data points at the same time, and that would definitely increase the throughput of the analysis of nitrate. Last, I'm just going to mention a bit about the outputs and outreach. The not underlined portions are the ones that are presented by Bruce, and the underlined portions are mine. So I've given several talks, even though those talks are not entirely on this specific nitrate work, but I mentioned the nitrate work in these talks. It's part of my research focus in my lab, which is on sensor development. And I'll be giving another talk in April. And in terms of the publication, I've already mentioned this nitrate publications. And hopefully I will also contribute to the website later on. And in terms of the manuscript for submission, there is one that I will be submitting very soon. We have developed a peptide-based lead sensor, and in 2017, hopefully I will be able to submit a paper on conductivity sensing, which is part of the proposed work. And thank you for your attention.